Hello class, welcome to our second lesson dealing with scale drawings in section 7.5. Remember, we want to be able to use some cross-multiplying techniques in order to find missing pieces, whether it be from the scale or the real-life model or drawing. We also want to look at the difference between scale and scale factor today. Before we get started with those topics, I just want to review some things about area. For example, the area of a parallelogram, this top left one, is base times height. What I like to do more and more is to give you extra info though. So like this 10.1 is needed for the perimeter of this parallelogram, but not needed for the area. So for the perimeter, this is 10.1, and so would this other slanted one, and then 11 would be the top and bottom. But to find the area, remember it's the base times height, and those things have to make a right angle when you find it. So it should just be the 9 times the 11, which would be 99 kilometers squared. For the triangle, same idea. It's base times height, but then divide by 2 because the triangle is half of the parallelogram. And so this would be the 3.7 times the 5 and divide by 2. This 4 is unnecessary. Don't always assume that the base is on the bottom piece of the picture because all I have to do is rotate it and now it could be on the side. Trapezoid area is 1/2 base 1 plus base 2 in parentheses, or the quantity of, and then times the height. So that's what I've done right here. If you don't know some of these area formulas, my suggestion would be find that information. It's in the back of your docket, for example, or online, and write those down to make sure that you have those ideas figured out. Okay, this information is right from your book. So scale drawing is for 2D objects, scale model, 3D objects, but really they're the same idea. And the scale is always the distance or a piece of the model or drawing first, and then the real life one. So in this situation, 1 inch is 10 miles. That could be something like a map. And what that's saying is 1 inch on my map is 10 miles in real life. So if something is really big in real life, the scale should be small to large. But if it's a vice versa, like say you're doing something in science class and you're looking at cells or an insect or something, it would be flipped, and the larger number would be first and the smaller number would be second. It's all based on the model or picture or scale drawing versus real life, though, when you're setting those pieces up. Okay, so this one is find the distance between two cities. So let's say it's from Cadillac to Detroit. Now this is going to be hard to do because the scale that you use might be different. So my assumption here was this is 4.5 centimeters. It may be different on your picture depending on your scale. That's really the least important issue right now. Okay, the important issue is, can you get a proportion set up? I know it's easy to solve some of these in other ways, but the proportion idea is what we would need to set this idea up and make sure on more difficult questions that it works. Now, in this case, what could be helpful is the scale key right here. So this key could help me realize, like, oh, that distance between the two, and when I find that, it doesn't matter how I've zoomed in my picture, as long as I have the scale key right here. Like this is supposed to be 1 centimeter, and on your screen it probably doesn't look like 1 centimeter because I've blown this picture up a little bit. And so that will still give you what you need for this situation. This answer is going to end up being 225 miles because in real life it's 1 centimeter is 50 miles in real life. The problem is this would mean you'd have to have a helicopter or something to get from A to B. If you've ever driven from a city to another city, or you've paid attention to a map, you'll know that you have to take certain roads and you're kind of stuck with the directions that you're going. So that probably would take even a little bit longer because of the way that the roads are set up. This one says the liquid outer core is 2,300, and then find the information based on this 1 inch to 500 kilometers. That one's in your textbook, so I'm going to let you figure that one out using your textbook. But then I added this one in. The mantle is 2,900 kilometers thick. How thick is the mantle? So I'm going to solve that one instead. And so I just use the scale. 1 inch in the model is 500 kilometers in real life. I don't know the model, but I know real life is 2,900. I cross multiply it. 2,900 equals 500x, divide by 500, and I get x equals 5.8. And then the unit should be whatever the units of the other one was. So since this is inches here, it's going to be inches here. Okay, so that would mean in my picture, it's 5.8 inches for the mantle of the model. And again, like I said, that first question is in your textbook, and you can look at that one yourself. The next thing we need to talk about is what's known as scale factor. Now, a scale has units. For example, like 1 centimeter to 50 miles, or the last one, 1 centimeter to 500 kilometers. A scale factor has no units, which means the units have to be the same so that they can basically cancel themselves out. Okay, that's the scale factor. So here's an example. Here's a monument from Sergeant Floyd, who was in the Lewis and Clark expedition. It's in this is in Iowa, and the monument is 10 inches tall in the model of the city, and the actual monument is 100 feet. So 10 inches to 100 feet would be the scale. Always simplify. Okay, simplifying that would be 1 inch to 10 feet would be the final scale of that object. The scale factor, though, has to have the units be the same. So if I have 1 inch to 10 feet, I need to change the 10 feet into inches by multiplying by 12 for the 12 inches in 1 foot, and then I get 1 inch for every 120 inches. Essentially what happens here is, you know how you can cancel numbers out from division? You can also cancel the labeling or the units out. So the inches cancel, and this is a 1 over 120, which means that the model is a 1/120th the size of real life. The benefit of scale factor is that idea makes sense. This is not 10 times smaller than real life or vice versa. Okay, this is 120th of the size of real life. Okay, so it's like you take that thing and shrink it down by a factor of 120 in each direction. Okay, that's where the idea of scale factor can become helpful. The next one says the drawing has a scale of 2 millimeters to 15 centimeters. What is the scale factor? So if it's 2 millimeters to 15 centimeters, you have to make the units the same. Well, for every 1 centimeter, there's 10 millimeters, so I just multiply that denominator by 10, and that would be 2 millimeters over 150 millimeters. I cancel out the units, and that becomes 2 over 150, which is a 1 over 75 scale factor. This means that the scale or the drawing was much smaller because it's 1/75th the size of real life. If these were flip-flopped, that means the scale was much larger, so it'd be something like something with cells or something with an insect, something really small that we were trying to blow up so we could see that. That would typically happen more in your science classes. The next one has the drawing of a computer chip. Now the problem with these questions is you have to measure them from your textbook. So again, you're going to have to measure some things from your book, so please make sure you have your ruler. This chip is 4 by 4, so 4 centimeters by 4 centimeters. Okay, the perimeter of the scale drawing would just be 4 plus 4 plus 4 plus 4, 16 centimeters. This is kind of a tough question because the area is also 16, but it's 16 centimeters squared. Okay, so 4 centimeters times 4 centimeters would give me 16 centimeters squared. The actual object, okay, if it's 1 centimeter for every 2 millimeters, if I set this up with a cross-multiplying idea, which I'm going to continue to do in case the scale becomes more complicated, would be 1 centimeter for every 2 millimeters is the same as 4 centimeters in my picture compared to real life. And in real life, that would be 8 centimeters by doing cross-multiplying. Now remember, 4 centimeters is larger than 8 millimeters. So my scale of this computer chip is larger than the actual computer chip. Those of you that are into computers would understand that because computer chips are really small. So the perimeter of the actual object is 32 millimeters, and the area of the actual object is 64 square millimeters. And I can just get that by taking the 8 millimeters and adding them up or multiplying depending on if it was an area or perimeter question. Okay, here's where the idea from the last class comes into play again. The drawing was 16 centimeters. The actual perimeter was 32 millimeters. And if I simplify that down, it becomes a 1 centimeter to 2 millimeters ratio, which is the same as the actual scale. Okay, so the scale should be similar for the perimeter. The area should be that squared, but I don't have to know that necessarily right now. I can just find both answers. So the actual drawing area was 16 centimeters squared. The drawing area, which would be my model, and the actual area was 64 millimeters squared. I simplify the 16 and the 64, and that becomes a 1 to 4, which is 1 squared and 2 squared. But again, I don't have to be an expert at that. I can just find the two areas and then divide them out and simplify. And that can be how you can be successful on some of those questions. Okay, your homework today has a couple definitions. Remember, those are in your textbook, so just flip back a few pages on questions like numbers 1, 2, and 3. 8 through 17, I want you to focus in on writing some type of cross-multiplying setup. Okay, don't just write, oh, the answer for number 9 is 4. The answer for number 10 is 8. Okay, set up a cross-multiplying even on an easy question. Please make sure you try that out as you're looking at your homework today. Have a good day, everyone.